Our guest today is Guru Chahal, a partner at Lightspeed focused on AI and enterprise infrastructure. He's been investing at Lightspeed since 2012, and he backs the companies building the picks and shovels of the AI era. We brought him in to pull back the curtain on the thing that everyone's arguing about right now, the data center. Guru, welcome to Lightwork. You have spent so much time across the AI stack, finding these picks and shovels across this current build-out that we're experiencing. But one of the things that comes up time and time again is the questions around data centers. They don't necessarily have a great reputation, and there's a lot of confusion about what a data center even is. So we're really excited to have you on to demystify all of that for us. And I want to just kick it off with just what even is a data center?
Well, first of all, thank you so much for having me. Data centers are one of my favorite topics. I'm an absolute geek at heart, and I nerd out about this stuff all day long. So excited to share some of this with you. So first of all, data centers are nothing new. They've been the anchor and a critical part of our economy for over 30 years. Everything we do in technology comes from a data center. You watched a movie on Netflix, that's a data center. Our audience watching this right now, coming from a data center. You do a bank transaction, that's a data center. You go to any website, being served from a data center. You buy something from Amazon, that's a data center. So they're just a collection of computers sitting in a large building, serving up our websites and technology and applications that we interact with. And this has been around for 30 years. What is different now, though, is that the importance of these data centers continues to go up, because we used to build these traditional data centers with servers, which are basically fancy word for computers and CPUs. And now we're building these new kinds of servers inside these data centers called AI servers. But other
What's
than that,
the difference between just like a data server and just like, well, the traditional AI, the traditional data center and maybe an AI data center?
So think of a data center as a factory. And the traditional data center was building sedans. The AI data centers are building race cars. That's a difference. It's just a different kind of product. We are putting in more powerful chips so we can do more computing inside these factories, inside these data centers. Now, these chips require more power. They require more cooling. They require more innovation. I think some of the confusion comes from the fact that you automatically and naturally sometimes assume, oh, if the chips require more power in an AI data center, that must be bad. If they require more cooling, that must be bad. But fundamentally, it's the same idea. There's just more innovation, more density, more compute inside an AI data center.
Maybe walk us through, for example, I watched this video that's about to play. How does that flow into a data center, and how might that differ from if I prompt ChatGPT once? How does that flow into an AI data center? What does that actually look like?
Yeah, so traditionally when you go to a website, you go over your network. That network hits a data center. Data center is a hard drive. There sits that little website. It serves it up, sends it over the network right back to you. So that's been, for 30 years, essentially how data centers operate. You go to a website, means your browser asks for the website, and from somewhere across the globe, there's a data center that has that website and serves it back out to you. AI data centers are slightly different. So you go to ChatGPT and you ask a question. It goes to a data center, again, same as a website. But inside the data center, a number of GPUs go over and they talk to each other. They generate all the tokens that constitute that answer to that query and then serve that back. So there's more communication inside the data center, more time spent, more computing spent to generate that answer. But fundamentally the same idea. You ask for a question, goes to a data center goes work and generates the answer, and you get it right back.
And it's this fundamental unit block for everything that the internet runs on. And we'll do a breakdown later on this stack and all the different layers. But I figured it might be nice to maybe bust some myths that I think we're seeing a lot in public discourse around data centers.
Yeah, there's so much discourse around, is ChatGPT drinking a bottle of water every time you prompt it? What are some of those myths that either are false or have some truth in them?
Yeah, the only thing drinking a bottle of water around here is me. It's not ChatGPT. Let me share a couple of statistics with you. I think it's important to ground this in reality first. As of a couple of years ago, here were the stats. US data centers as a total were consuming about 17 billion gallons of water. 17 billion gallons. That might seem like a lot. the average almond growth here in California consumes about 4 gallons a day. So that's about 4 days of almond water. That is the entire year's worth of water consumption by data centers. So these numbers are small by comparison. But even better, and more importantly, the next generation of these AI data centers are closed loop systems. It's not like there's a river flowing next to the data center and you tap into it and cool the data center and hot water comes out. These are closed loop systems. Once the data center is up and running, the water just gets recirculated within the system. And so there's actually very little consumption. In fact, just this past week, NVIDIA's announced some amazing developments in its Vera Rubin architecture, where even instead of water or in addition to water, they are running coolants. You know, the kind of coolant that's in our cars? They're running coolant to actually cool these data centers, completely closed loop. It's almost no external water consumption. So we are rapidly approaching a world where the impact, water impact, which is already negligible, is approaching zero. So that is definitely a myth.
And to take a step back, why is water and cooling even involved in this process?
So these things run hot. So if you ever use your laptop or computer and run a very compute-intensive workload, you'll notice it gets hot. Your phone gets hot, if you're playing a very intensive game on it. And so these servers are the same way. It used to be that the non-AI data centers would run about 10 kilowatt of power. That power eventually converts itself into heat. AI data centers can consume 10 times that on a per rack basis. And so you could have 100 kilowatts. So these things get pretty hot. Not as hot as an iron inside your home, but still pretty hot. And that needs to be cooled. So old way of cooling, you run a big fan and it forces air through the system. In fact, you can stand in these data centers so loud and that air would just take all the heat away. But these newer data centers require even more removal of heat. And that's where liquids and coolants and immersion cooling come in, which is actually great for the environment because now you have these closed loop systems. You're not even blowing hot air into chillers. You don't have chillers in some cases. You can just recirculate coolant through the system without any chillers at all, which is very power efficient. So exciting times in this space.
Well, there's so many of these data centers and there's so many concerns about power in America. What's the implications? Like, could any of these crash the grid? I feel like folks are, in general, they're not just worried about water. They're worried about, can they power my house or is the data center down the street going to take it?
Yeah, that's another myth. So let's break it down to numbers. About 4% of the US power consumption till a couple of years ago was going to data centers. By the end of this decade, maybe that goes to 6%, 8%, maybe even 10%. But that's not net new power. That is power that was not being utilized typically in areas that are far away from the metros. So this is not like, you turn on the data center and my home power goes down. These are data centers in the middle of Texas, as an example, or other places where the grid does have spare power that can now be redirected towards data centers and towards productive use in the economy. The impact on house power is even further reduced thanks to some of the efforts that this administration has taken. And increasingly, these data centers are being built with behind the meter power, which means if I build a data center, I'm responsible for generating my own power in many cases. So the expected impact on residential power rates has very little to do with data centers. It has to do with the fact that, for better or for worse, we have a grid that is over 50 years old and someone has to replace it and renew it and revitalize it. That costs money. So there could be some impact on residential prices because of that regular revitalization of the power grid. But it's very little of that has to do with the data centers that are coming up.
I think one of the more exciting forward-looking parts of this is the fact that AI itself, it might even drive some innovation in the data center world. But I'm curious if you're seeing some of that in the energy spaces, the reactivation of nuclear. I think innovation's coming to the grid. Where are you seeing renewed excitement and innovation because of the quote-unquote data center issue?
Yeah, so this is another thing I'm very excited about. It's a circular thing. AI is produced in data. So data centers produce AI, and then you can use that AI to make data centers even more efficient. So about 10 years ago, Google started this incredible effort internally on really directing their own machine learning and artificial intelligence systems on their own data centers, say, make this more efficient. And turns out they made their data centers 40% more efficient back in 2016, just by having AI study the utilization of power and utilization of cooling in those data centers and further optimize it. Meta did the same thing back in 2021, 2022. So I expect more of this to happen where data center operations themselves become a lot more efficient thanks to AI. Another area we're quite excited about is the use of AI to develop new materials, materials that are naturally much more power efficient, materials that are much better at cooling. Another area where we've made some investments that we'll talk about later are how do you design systems and chips and hardware that naturally is much more efficient and utilizes less power to do more in AI. So very exciting times in how data centers are not just producing AI, but that AI then produces more of itself by making the data centers much more efficient.
Yeah, I think that the Google initiative was one of the first times that I was introduced to this idea of AI as iterative intelligence. Obviously, we've seen that with auto research and on the software front, but actually even just seeing it come downstream into our physical world and just even seeing the ways that AI can unlock efficiencies in its own stack, which is really exciting. I think maybe to end, I interface with a lot of people through my content, and I guess I'm curious if you're speaking to a young person who is really concerned about the environmental damage of this technology. It's one of the reasons they're abstaining from it. Do you have any advice about how to think about usage of AI, about how to contextualize it? I know you brought up the almond example. The other one that comes to mind is golf courses, or even, the CO2 emissions from an airplane are significantly more than ChatGPT usage. So curious how you're thinking about the evolution of this narrative and whether, the timeline you think we'll see improvements from an environmental standpoint.
Yeah, so I'll share with the audience the same bias I've always had and the advice I give to everyone, which is you have to recognize the incredible power that technology broadly represents and AI in particular offers to us. We can do such incredible things with it. For fixing the things that you might be worried about, it's more important to participate in this world and adopt it, and then from the inside make it more efficient than it is to abstain from it. You don't do the economy any favors by not driving a car because you're worried about its impact on the economy and instead using riding a horse everywhere. That doesn't help anyone. What does help is by understanding how cars work and then helping that movement from internal combustion engines to electric vehicles. So abstaining is not the answer. And I think what folks in the audience would find is AI is the answer to actually making a lot of these things better. We can't solve climate by ourselves. We can't solve power issues by ourselves. We can't solve cooling issues by ourselves. We need the extended brain power that AI represents to solve some of the most profound challenges in front of humanity right now.
I think my takeaway is I'm going to start putting Claude in my coffee instead of almond milk because it might be better for the environment.
Let me know how that goes.
Should we spend a little bit more time actually walking through the stack and where we are seeing exciting innovations?
Let's do it. Let's demystify this whole thing.
Please take us through the factory floor of the AI revolution.
Perfect.
Okay, so we have the data center, which you've broken down for us. And you mentioned a lot of terms that we've laid out here. And we've broken it down into 7 layers, from kind of the most basic things that you need to all the way up to compute when we talk about things like NVIDIA, GPUs. And we figured it might be helpful for you to break down each of these layers, why they matter to the data center, and where we might be seeing some innovations and exciting companies across the stack.
Perfect. Let's do it. Let's demystify what an AI factory looks like. This is how you build a data center if you were building it from scratch. So step 1, you need space. You need a big shell. That's a big box that you see when you think about data centers. So you got to identify the land. You got to build a shell, and you got to figure out how many racks and how much equipment you got to put in. Now, to give you a sense for the size, these could be multiple acres large. So these are big, like football field, multiple football field size shells that you create. So that's a land shell. Then you load in racks. these big sort of racks inside where you will put all your computers. And then, of course, the physical security, because look, at the end of the day, it's very expensive equipment. It's also running some critical applications like your banking application. And so you want to make sure no one can walk in and steal that data. That's the data in a data center. And so that's step one. Next come these two critical pieces. So you got to power this thing up, just like your house. You built a house, you got to power it, you got to get the air conditioning in. And so that's next. Cooling is your typically liquid cooling, which is becoming more common. Instead of just blowing air through the data center, you're driving liquid through pipes to wherever heat exists. So you can then take that heat out and recirculate that. Power, of course, is the power that powers all of the stuff in. This typically comes from either the grid, from a transmission, comes to a big transformer outside the data center. That's a lot of power. And then almost think of that transformer breaking it up into smaller power at different current and different voltages and punching that into the data center where it powers different devices. Increasingly, interestingly, and this is why it's a myth to say that this has a huge impact on residential power. Increasingly, data center providers are required to generate their own power and negotiate their own contracts with the power generators. So you take care of power and cooling. So now you're done. This is your structure of the house, your shell's there, the box is there, it's powered, and you're ready to go. That takes us to the next four major layers here. Storage, that's where the data is actually resides. That's your hard drives, just no different than your hard drive in your laptop. That's also the working memory, etc. Then a piece that we are very, very excited about, which is networking. This has become extremely important because AI workloads are fundamentally different from your regular traditional websites and workloads. AI workloads are very chatty. They talk to each other a lot before they generate that answer that you and I see when we ask Claude a question. And so for all of that communication to happen, there needs to be a great network in place. And so the importance of network has gone up by orders of magnitude in these new AI data centers.
And I've always thought of those as sort of like transportation lines for the chips to talk to each other.
That's exactly right. And they exist at every scale of the data center. It's from chip to chip, it's from server to server, rack to rack, across the entire data center, and even between data centers. So this communication is becoming very important. And then the final two pieces are what we think of as servers and computers. Memory is the same memory that's in your laptop, except much more powerful and much more capable. And then, of course, compute is when we think of NVIDIA and AMD and Intel. That is typically two different components. One is the CPU. That's very similar to the CPU in your laptop. And then the GPU, which is where the AI workloads, the different machine learning models, they all run. So those are supplied by NVIDIA, but also a number of other companies.
And so a clarifying question, it sounds like this is all the physical stuff.
Yep.
This is the computer part.
Yep.
And so for the computer part, what does that look like? Is it a bunch of, how do the GPUs and CPUs and the networking and the memory layer all fit in? What does that look like physically? How does that stack look like?
So the shell we understand. It's a big building with these racks of equipment. So the question is, what goes inside these racks? So think of your laptop, stretch it out a little bit to about this big, and then make it thicker, about this big. So that's the shell. That's what we call a server. Inside the server go the CPUs from AMD or Intel or ARM. And then next to those sit typically 4, 8, sometimes even more what are called GPUs or AI accelerators. All of that is inside this one box. And this one box can consume several kilowatts, over a kilowatt of power. So it gets hot. And so these things are just stacked. So you walk into a data center, you see this big rack, and there's this box after box after box after box. Typically in the middle, they'll put a network switch to connect all the boxes together with wiring. Those are the big yellow cables you see in data centers. And then, of course, you got to cool all of that up. So it looks like, imagine a super neat closet in your home.
Okay.
That's not my closet, but a super neat closet and just neatly stacked stuff inside that closet. That's what it looks like. And all of this, by the way, what's exciting is this represents trillions of dollars of infrastructure. All of this is seeing incredible innovation. Right down here, how do you find building sites? How do you identify those? There are incredible founders working on those. We've been very focused on power and cooling.
Okay.
How do you ensure that you can power these data centers in a way that doesn't impact residential workloads. We have a company named Base Power, which is doing some incredible work here. Think of Base Power as building a virtual power plant in residential neighborhoods. So I'm sure you have a battery outside your house, you have solar power, you have batteries. What if you could connect all of those batteries in residential neighborhoods together? So they essentially become a power plant that can power the neighborhood itself. That reduces the load on the grid, which means your impact of any particular data center on the residential grids is de minimis. And so we're very excited about what Base Power is doing. Another company that is doing some incredible work in this space is a company called Periodic. Periodic is an AI materials company. So they use very powerful AI models to find new kinds of materials that can cool things better, materials that might be more power efficient or conduct electricity better or help make supercomputers more real, more accessible. And so Periodic and Base Power are doing a lot of work at this physical substrate layer. And then we're pretty excited about what's happening up here. I mentioned networking earlier. Networking has gone from 5-10% of the overall spend when you build a data center to over 15% now. That's how important it is because you got to connect all of these things together. And so the two questions become, how do you connect them in a very high speed way? So these freeways, they need the ability to move lots of data back and forth, but you also need to do it in a power efficient way. And that's where one of our companies, Nexthop, comes in. And this is an incredible team that is building network switches that not just connect everything together, but do it in a way that is typically 10-15% more power efficient than the average switch out there that you would buy in the market.
And as you mentioned, AI data centers just have a lot more networking. So you have to deal with higher volume, but also introducing more efficiency, which
That's
Nexthop
exactly
does.
right. So very excited about the innovation that Nexthop is bringing there. And then that brings me to really the brains of the system. This is where your AI models are running, that compute and memory piece inside that server. And there, again, we are very focused on how do you make sure that you can not only bring intelligence to the market, but do it in a very efficient way, consume as little energy as possible. And we're very excited to work with two companies in this domain. One is a company called Unconventional, and they are exactly like the name suggests, very unconventional in their approach. They are building these AI brains or AI chips that are somewhere between 2 to 3 orders of magnitude more power efficient. So 100 to 1,000 times more power efficient. So imagine the same power, that same Claude query, the response that comes back, what if you could generate it with 10% or 1% or 0.1% of the power consumed?
And I
They're
think
working on incredible technology there.
something about Unconventional that I've always been drawn to is that they're basing these off of how human brains work, right? I think I've always been fascinated by the idea. He always mentions that the human brain takes like 5 watts of energy to
5 to 20 watts. It's a million times more efficient than the compute we have in data centers today. It's a lot of room for improvement. And this is a team that has that background. They've studied the brain, they've built silicon and semiconductors, and they built chips, and they've built software. So they're building a system that is just so much more efficient.
So they're trying to make chips a little less like traditional computers and more like the human brain.
That's exactly right. And then the final company I'll mention here that we're very excited to work with, how do you build more and more chips and run more experiments faster? Today, building a chip is so expensive. It takes $100 million to build that first chip that can run AI models. $100 million.
So when
bring it down to 10 or maybe even $1 million.
When NVIDIA talks about launching Blackwell, that $100 million, how long does it take to develop these chips even?
2 to 3 years to develop the next generation of chip, and over $100 million at the cutting edge technology today. And we're working with a company called Ricursive, which is, again, using AI to build chips much faster. Instead of 2.5 years, perhaps in less than a year, less than 6 months, maybe even a matter of months, and in a much more cost-efficient way. And so you can see these things start to build on top of each other. Now, what if Periodic builds materials that are so much more power efficient that they generate very little heat, and other materials that are great at then taking that heat and removing it from the system? That then enables Ricursive to experiment with so many more chips and design so many more power efficient chips on designs that Unconventional is building. So the whole system starts working on it's this compounding advantage over time. So I expect these AI factories of tomorrow are going to be 10 times, 100 times, 1,000 times more power efficient than even the AI factories of today, which are already significantly more power efficient than the traditional data centers we've been operating.
Yeah. And I think what my takeaway from all of this is that whether it's design itself or materials or efficiencies in the space, every part of this, there's something to be improved. And all these companies are attacking it from different angles.
That's exactly right. And now let me share the coolest part with you, which is what happens if I draw a line right here and take all of this fun stuff, package it in a satellite, and send it up to space. Gets even better. And so no building, no land, no shells, nothing. You take the basic brain and you package it up into a satellite, put it up in space, and guess what space has a lot of? Space. Lots of space, lots of satellites, amazing amount of power, radiant cooling. So we're pretty excited to see where SpaceX and other really innovative teams are going to take data centers as they take those up into space.
A couple of questions where I've heard some skepticism around the vision for orbital data centers or, space-based data centers is one, the radiation problem. Is that solvable? Is that, it sounds like, for example, even Google with Project Suncatcher, they're working on that. That's one question that I've always seen. The other one is the feasibility of the transport part. How are we getting these data centers up into space? It sounds like SpaceX has a solution with their rocket company as a transport company. And then the third one is just servicing and maintaining these data centers in space. How are you thinking about those three big questions?
So let's start with the two questions around compute in space and radiation and power and serviceability. We've been sending compute in space for 70 plus years. Every satellite ever that is up in space is running a CPU, is tapping into sun's power, is removing that heat from the CPU using radiant power, and has been handling radiation issues for years. I mean, Voyager, today, those satellites are beyond the solar system. They're still pinging us. Imagine how little sun goes out there. Imagine how much radiation there is in deep space. They seem to be fine. So again, I'm not minimizing the technical challenges, but they are very much solvable and have been solved at a different scale already over many, many decades. So the question of can you run a GPU or a CPU and a satellite up in space is a foregone conclusion. You obviously can. The real question is the one that you asked, which is, can you do it in an economically feasible way? Which is, can you get it up there cheap enough? That's question one, and probably the biggest question. And second, when you get it up there, how long is it going to continue to operate and how do you service it? The first question is really the main question. If it cost zero to put compute up in space today, space would be significantly cheaper because power is free and cooling is free. And you can handle the serviceability issue by looking at the life cycle of these things and just deploying a little bit more. Maybe you deploy 10% extra. Maybe you deploy 20% extra. If power and cooling are free, what do you care about putting in a little bit more hardware out there?
Shift all that up here.
Shift all of that up here. So that's the easy part. The big part is what SpaceX and other launch companies are able to do in terms of bringing the launch cost down. So that's the big, does that happen in 2 years? Does it happen in 5 years? And as it happens, we're going to see some incredible amount of compute up in space, which is exciting.
Yeah, I love that. In the way that we've had data centers for the last 3 decades, we've also had technically space data centers. I mean, space computers at least.
Forever. The first satellite up there had a CPU in it. You need it. It's not like, there's a little monkey sitting inside the satellites trying to type responses back out to you. So GPUs work in space. CPUs work in space. Compute works in space. There's enough power. There's enough coding ability. There are engineering challenges to solve, no question about it, but they're very much solvable with enough focus and brain power and AI helping us. The big question is how quickly can we reduce the launch costs to get all of this hardware up in space in a cost-effective way.
Yeah, whether it's all of these companies or space-based data centers, there's a lot of exciting stuff. And hopefully we'll do a follow-up episode when some of these are a little bit more developed too.
I would love that. This is the most exciting time to be a hardware nerd. I love and live in this space. Would love to come back and share more.
Thank you so much, Guru.
Thanks, Gary.